Today we'll discuss functional programming. As we've discussed, in our early classes, the programming paradigms, right? Classified into four, we said, right? Imperative, functional, logical, object-oriented initially, right? So we have seen many of them. Imperative, we have seen object-oriented, we have seen logical, we have seen. Today we discuss functional programming languages. If you probably look at the functional programming languages, they're based on mathematical functions. Right. Unlike imperative language, which is based on one given architecture, and it is basically more action oriented. The other way around, I can say, where you give certain instructions. The instructions are going to be executed in sequence. The more you are concerned about, the efficiency rather, right? Whereas if you come to the functional programming language, it's a solid theoretical basis that is also closer to the user, but relatively concerned with the architecture of the machine on which programs will run. What is a mathematical function? A mathematical function is a mapping of members of one set called domain set to another set called the range set. Okay, so you will try to map the values from domain set to range set. Okay, so this mapping is being done through the functions. Okay, fine. So a mathematical function is a mapping of members of one set, which is said to be the domain set, to another set called the range set. A lambda expression specifies the parameters and the mapping of a function in the following form, right? So if I have a lambda expression like this, fine, which specifies the function, this lambda is going to specify the function, okay, the parameters that you're passing to the same. So the second, parameter that you have is nothing but the, which are being mapped to certain mathematical function. Okay. So, for example, if I have cube of x, okay, this is the generic form which we have defined with the help of lambda, right? So, if I have to find, let us say, cube, so this function is suitably defined for cube. So, I can replace this lambda with cube of x equal to x into x into x, right? So the interpretation of this function, is nothing but cube of x equal to x into x into x. Lambda expressions describes the nameless functions. When you are not clear about the name of the function, like anonymous functions, which we call in Java, ADA. So those kind of functions, nameless functions you can define with the help of lambda expressions, right? So with the help of this lambda, you can be able to, define the mathematical functions, right, which are rather required to be carried out based on certain parameters that you have passed, to this particular nameless function. Lambda expressions are applied to parameters by placing the parameters after the expression. For example, here you have a lambda expression, a lambda of x, followed by x into x into x, right? And you have given a value of 2. Now you can see this is an instance of the expression. It is something like very similar to that of your anonymous functions of Java, right? Where this function is going to be here the other way around. I can say the function is defined and then being evaluated for an instance called 2. Okay, so here this function being defined with a mathematical function of x into x into x, and we want it to be rather evaluate for 2, fine, instance 2. So it is something like defining the function and executing it for certain values can be done together, at a stretch with a single statement, right, using this nameless functions, right? So if I have this 2, So the second parameter will be passed as an value for the first, right? Where the 2 will be taken for x and will be evaluated for this particular mathematical function, which is going to give you the result as 8. Okay. Functional forms. A higher order function or functional form is one that either takes function as parameters or yields a function as its result, or both, right? A functional form that takes two functions as parameter and yields a function whose value is the first actual parameter function applied to the application of second form. Like when you have multiple functions, right, to be set as parameters, then what happens here is the second parameter will be evaluated and then that will be sent as a parameter to the first function rather, right? For example, generally in mathematics you call this as composite functions rather, right? So H equivalent to F circle G is being interpreted as H of x is equivalent to F of G of x. So it means that this x is a parameter which is being sent to the second parameter or second functional form, right? And that second functional form which has been evaluated when that is going to be passed as a parameter to the first functional form, right? When you have multiple functions, right, composite functions, right, the second function will be evaluated first and that is going to be passed as a parameter to the first function, right? For example, if you have, let us say, f of x equal to x plus 2 and g of x equivalent to 3 into x, and the composition of these two functions, how that it is going to become is like, the 3 into x will be passed as a parameter to f. So wherever x you have in f function, that will be replaced by the evaluated form of the g, right? So then it will be interpreted as 3 into x plus 2. So f circle g of the functions which are defined before are going to be evaluated to 3 into x as one entity, which is going to be x of this f rather, right, plus 2. Okay. A functional form that takes a single function as a parameter and yields a list of values obtained by applying the given function to each element of a list of parameters, right? For example, if I have, let us say, when you want to apply the function to all the values rather, right, then you can go with this, alpha, apply to all. So let us say, for example, you have a function h of x, which is defined to be x into x, okay? Now, I want to apply this function on multiple values like 2, 3, 4. So in that case, you can use apply to all. Alpha of h of 2, 3, 4, if I say, then it yields to 4, 9, 16. It means this function is going to be applied to all these parameters. And the result will be yielded to 4, 9, 16. Because 2 into 2 is 4, 3 into 3 is 9, 4 into 4 is 16. Fundamentals of functional programming language. The objective of the design of FPL is to mimic the mathematical function to the greatest extent possible. The basic process of computation is fundamentally different in an FPL than in an imperative language. In an imperative language, operations are done and the results are stored in variables for later use. Okay, in imperative like C, C++, in imperative programming languages, where you can see you can store the result after the operations that you carry out rather, right? But here that is an issue. Management of variables is a constant concern and source of complexity for imperative programming languages, right? In an FPL, variables are not necessary, as is the case in mathematics. You can straight away pass the values for the parameters which are rather going to be substituted in that mathematical function. Referential transparency. In FPL, the evaluation of function always produces the same result given the same parameter. When you give certain values or certain parameters, the result which is going to be obtained is going to be the same when you pass the same kind of parameters next time. Fine. It means the parameters are going to be mapped through reference, right? Fine. So referential transparency is going to be taken taken as a primitive while carrying out the operations of that particular mathematical function. Fine. And another thing that we can find here in functional programming language is the tail recursion. Fine. Recursive functions you must have seen in imperative or structural kind of programming language, where recursion is something like calling a function within itself, right? So, but then you can see, let us say, for example, you take C programming language, where how do you return from the recursive function is at the end you probably terminate it with the help of certain constraint. For example, if you are writing the factorial of a number, recursion for the factorial of function, how do you let us write the factorial function in C. Okay, so you can see here you are passing some value. For example, when you are calling this same in the main function, five or four, whatever. Fine. So when you're passing, let us say 5 here, what happens that 5 is going to be, passed as a parameter for this formal variable, then that 5 is going to be checked here, right? So if 5 equal to 0, it returns 1. Otherwise, what it is doing, it is, going to the else part where you have n into fact of n minus 1. N into means 5 into fact of 4. With 4 again you go. And then again you check if it is false again. 5 into 4 into, then with 3 you go, and then you go with 2, then you go with 1. Then when you go with 0, you return 1, so 1 into 1. So it will be almost 120 rather, right? But you can see here, you are returning at certain point, right? You are returning here by checking certain constraint, saying if n equal to 0, you return with value. So you are exiting from the recursion through some value rather, right? Or through some iterative statement rather, right? This is an iterative statement. So you are exiting here either through some value, fine, or sometimes you may return because of passing the value which is not being rather satisfied here. Okay, but in functional programming language, we have an option of tail recursion. Tail recursion in the sense you end through a recursion. I mean, this is our exit point, right? In the exit point also you can have recursion here, right? This is not recursion. See, if n equal to 0, return 1 means you are just returning 1. This is not recursion. Whereas here this is recursion because calling the same function, right? You can see the function name is fact. See, you are calling that fact here, right? So in else part you are having recursion, but in if part you don't have recursion, right? And if part is the point of exit in this case, right? So, but then in functional programming, if you go with where the exit point can be a recursion, it means here also you will be calling the function, right? So, but then who are going to take care of that recursion? Of course, the compiler of the programming language, right? So that converts that recursion into the respective iteration. Fine. So the tail recursions, which made the functional programming language more efficient while writing the code, rather, right? It is more meaningful and then readable, rather. We'll see with examples probably when we move ahead with some programs. Now coming to the data types and structures that we have as part of the functional programming languages. So we'll find there are two data types majorly. One is the atom, another one is the list. Okay, so there will be only two data types you will find: atoms and list. The list form is parenthesized collection of sublist or atoms. Fine. The atoms can be basically some alphabets, right? Like A, B, C, D, E, you have given, right? Or it could be digits sometimes, right? Originally, list was typeless. So it means here you don't mention that value of that atom. It could be integer, it could be float. So automatically, the kind of value that you give for the particular respective atom, it will take it, convert it into the respective form. Fine. So because of which we say it is a typeless, right? Lists are stored internally as single links. The data structure that it is making use of to store the list is linked list data structure. Right? In data structure, you have studied already linked list concept. So in linked list, you will be having one root node or head, right? Okay, and then the subsequent nodes are pointed through this root node, rather, right? You will have a pointer, which we call it as next pointer, right? Or link, you call it as. So that pointer will hold the address of the next node. Subsequently, further nodes will hold the address of the subsequent nodes. Like that, you will have, and then the last node, next pointer will be null. Fine. In order to perform any operation on this particular list, from where do you start with? You start with root. Root is a special static pointer which holds the address of the first node. So to do any operation, you start from the root. Okay. Okay. So the same kind of structure or the application of the linked list, you can say, is what the list of the list. Okay. Lisp stands for list programming. List program. This is one of the first functional programming language ever invented, right? In the function programming language domain. Okay. Lisp. Lisp is an interpreter based, okay? Like we have discussed in early classes, we generally find a compile based programming language and interpreter based programming language from the translator point of view. C, C++ are the compile based, because we have a compiler, it converts the high level into a low level, okay, using the compiler. Whereas Java is an interpreter, is a mixed, I said, right? It is a hybrid kind. You have first compiler, then interpreter. So similarly, Lisp is a pure interpreter based, right? You have interpreter here to convert the high level into the machine level code, rather, right? Lambda notation is used to specify functions and function definitions. Function applications and data have the same form. If the list of A, B, C is interpreted as data, it is a simple list of three atoms, A, B, and C. If it is interpreted as a function application, it means that the function named A is applied to the parameters B and C. Fine. So if you have a list of three atoms here, A, B, C, A is found to be the function, and the subsequent two atoms are considered to be its parameters, right? For lambda functions, when you are probably defining, rather, right? The lambda function also can be consider as a list, right? The first atom of the list will be considered as the Lambda function, and the subsequent two atoms are considered to be the parameters to be applied on that respective function. Okay. The first Lisp interpreter appeared only as a demonstration of the universality of the computational capabilities of the notation. The first dialect, the dialect of Scheme is one of the first dialect of Lisp actually. It is found somewhere in mid-1970s, designed to be a cleaner, more modern and simpler version than the contemporary dialects of Lisp. And it uses only static scoping. Functions are first-class entities here. They can be the values of expressions and elements of Lisp. They can be assigned to variables and passed as parameters. Evaluation of the same. The parameters here are going to be evaluated in no particular order. The values of the parameters are substituted into the function body. The function body is evaluated. The values of last expression in the body is the value of the function. Primitive functions that you find here are arithmetic, like plus, minus, into, divide, absolute, square root, remainder, min, max, and all. So here the functions are represented as a list of three elements. The first one is considered to be the function. The subsequent two other parameters for binary operation, right? So if you have a function to represent the addition of two numbers, you can use this. So here everything is a list, of course. So the list here consists of about three items, right? The first one is the function, which is being represented with the help of symbol plus, and you have two parameters to be sent to this particular function, or rather to be applied on this, rather, right? So 5 and 2, which yields the result as 7, because it is interpreted as 5 plus 2, okay, which yields as 7. Quote is another kind, which generally returns the parameters that you have sent to that particular function. It takes one parameter, returns the parameter without evaluation, right? If you want, is a similar kind of your buffer gate, rather, right? So quote is required because the Scheme interpreter named eval always evaluates the parameters to functions applications before applying the function. So in order to convert, basically you require this, rather, right? Quote is used to avoid parameter evaluation when it is not appropriate. Quote can be abbreviated with the apostrophe prefix operator. Apostrophe A, comma B, A B. You can represent like this. Fine. Is equivalent to quote of A, comma B. So it's going to return it as a parameter, right? Lambda function. Lambda expression, as I said, is a nameless function which can be rather used to define some mathematical functions. Here you can see, for example, if you want to represent square of a number, you can use this lambda. So the list here consists of three items. The first one is the function. Here it is consisting of about two parameters. First one is the function. Second one is the definition of the same, right? And here the first function, which is nothing but lambda of x. Here in the second atom, we are defining the function with the help of mathematical function, that is x into x, right? So this x into x here we have represented with the help of a mathematical function as a list here, right? So now you can see the evaluation of the same, you can represent it with the help of three atoms now. Fine. So this list consists of about three atoms. First one is the function name, second one is the definition of the function, third one is the parameter applied on the particular function. So here what is happening, you are defining the function and evaluating the same for certain parameter, right? So the result of the same will be obtained as 49, right? The lambda of x is the function name, and the definition of the same is x into x, and the parameter to be applied on the same is 7. Defined. This is a special form of the function which we can probably use to define certain constants or to define certain functions as well. Fine. So like how in C also you have a macro function. You generally define with the help of define. Very similar to that, you can use this define functions. To bind a symbol to an expression, you can use this define. If you want certain values to be constant throughout your program, you can use this define pi 3.14 kind of thing. So this pi will be binded with this particular value throughout your program. Or if you want to define it with 2 pi and all kind of thing, you can probably go with define 2 pi into 2 pi. So this pi, which is being taken from here as 3.14, substituted here in order to get the 2 pi value, which is going to be evaluated to be 2 into 3.14, right? To bind the names to lambda expression, you can use define to bind the names to the lambda expressions as well. For example, define square of x into x, right? So if you pass square of 5, what happens? It is going to return you as 5 into 5. The evaluation process for define is different. The first parameter is never evaluated. The second parameter is evaluated and bound to the first parameter. So first is the definition, of course, rather right here. Second one is going to be evaluated for the same function which you have defined before. Output functions like display, we can use display followed by expression. If I want new line operator, you can use new line. Yeah. Numeric predicate functions. Generally, the predicate functions as a based on certain predicate calculus, which rather results with true or false. Fine. For example, here most of the expressions which you rather evaluate to obtain either true or false, you can use this predicate function, right? So true, the hash t is the true value, hash false is going to be represented as a false value. Sometimes open parenthesis is used for false also, fine. So certain predicate functions you can rather use to evaluate on certain parameters and return the value after being evaluated to be either true or false, like equal, not equal, greater than, less than, greater than equal, or less than equal. There are certain, predicate functions, which we generally call it as relational operators in imperative programming language. Even you want to check whether it's a even or odd or a zero or negative kind. Also, you have certain functions of built-in kind in Scheme. You can directly make use of that same, right? Coming to control statements, the control flow of Scheme is being maintained through if statement here. This is one of the selection statement that we have. So how do we use this? If predicate is the condition, of course, the expression which you have, then expression to be evaluated, else expression to be evaluated, right? For example, if you want to check here count value, if count value is not equal to 0, this is being used for not equal, right? So how do you interpret this? If count is not equal to 0, you want to evaluate with division operation. And what are the parameters for the same? Sum and count. So it's going to be evaluated as sum by count, right? If count is not equal to 0, sum by count, or else it is going to be 0. Returns as 0. Another conditional operator or control statement that you can probably use as part of Scheme is COND, conditional. So this can be used as a multiple selection also. Fine. Very similar to that of your if else if or multiple if or switch case kind. So here this conditional control statement, how it's going to be used is you write COND, then the different conditions that you have followed by it you're going to mention, and upon each such predicate being found to be true, what is the expression that you want to evaluate? You're going to mention it, rather, right? So how do you represent it? You can see the general syntax of the same. Mentioned here, condition followed by predicate 1 is one kind of condition, right? Which is going to be evaluated, and based on its truthness, you are going to execute this expression, right? or else if this is false, then other predicate you must be having, which is going to be evaluated, and if it is found to be true, then you're going to evaluate expression followed by the same. So likewise, you can have any number of predicates or conditions, right, based on which truthness you can rather execute different kind of expressions, right, and none of them if found to be true, then you can go to the else part where you can execute the expression followed by the particular else. So return the value of the last expression in the first pair whose predicate value evaluates to be true. For example, let us say you want to compare two variables x and y. Okay, so here you are defining the function with the help of define define compare of x comma y, and then in this function you are using the control statement with the multiple selection, that is conditional here. So this condition is having first predicate is to be evaluated to check x is greater than y. If x is greater than y is true, then it is going to print x is greater than y. Okay. If this is false, then it checks the x less than y. If x is less than y, then it defines y is greater than x. Fine. If none of this condition is true, then it's going to execute the else part where you are saying x and y are equal, right? Then we have certain list functions to be available as part of scheme, or cons and list, right? Basically, when you want to combine certain elements into a single list, you can use this cons operation. It takes two parameters, the first of which can be either an atom or a list, and the second of which is a list. It returns a new list that includes the first parameter as its first element and the second parameter as the remainder of its list. The interpretation of it here you can see demonstrated with the help of an example. Cons A, B, C, right? The apostrophe of A is nothing but quote of A, which returns A itself, and this apostrophe of B, C is nothing but quote of B, C, which returns same B, C. So here cons is going to take A as the head, and the second is going to be considered as the remainder of the first list, right? And it generates it as a list. So what this cons operation will be now going to generate for us is nothing but a list of elements considering the first parameter as the head and the second parameter as the remainder part of the same. So it consists of now A, B, C. Okay. List takes any number of parameters, returns a list with the parameter as elements. Okay. The functions that you apply on list, like basic operations, are car and CDR. Car is the content address register. The abbreviation of car is content address register. CDR abbreviation is content decrement register. So car takes a list parameter, returns the first element of that list. So if I apply car or CDR on the list operation, here we have demonstrated with some example. You can see here first with car. So if I am applying, let us say, car on a list of A, B, C elements, what it returns? It returns me the first element of the list. What is the first element of this particular list? Out of this A, B, C, A is one element, B is another, C is another. So these are the three items we have in the list A, B, C, right? So when I have applied car on this particular ABC list, the first element of this particular list is A, which is going to be returned as a result of the same. Fine. For example, if I have a list of, let us say, AB and CD. This AB, though it is a list, but here it is considered as an atom or an element, right? And then you have C and D as other elements. So when you apply car on this, what happens? It returns the first element. First element is nothing but AB, which is nothing but a list itself, rather, right? So AB will be returned. CDR is content decrement register. It takes a list parameter, returns the list after removing its first element, right? So it means it will remove the first element from the list and then returns the remainder part of the same. Fine. For example, if I apply CDR on this ABC list, right? So in this ABC list, removing the first element, that is A, the remainder part is carrying with two elements, that is BC, will be returned as its result. So the result of CDR of ABC is nothing but BC, right? Similarly, if I apply CDR on this particular list here again, AB is one atom here, though it is a list, and then the subsequent elements in that list are CD. So when you apply CDR on this, what it returns? It returns the list remainder part of the list by removing the first element. The first element is AB, which is nothing but a list, of course, right? It removes this and then returns the remainder part of the same. The remainder part of it is nothing but CD, right? Now coming to EQ. EQ is a predicate function here which takes two symbolic parameters. It returns true if both parameters are atoms and the two are the same. Otherwise, it returns false. Basically, this can be used to check the list and atoms, right? So equality symbol here we have used on, let us say, these two lists, A and A. Fine. So here you can see A and A, both are, same. So it returns what? True, of course, right? If you are applying equality symbol on, let us say, A and B, it returns false because they are not same, right? Note that if EQ is called with list parameters, the result is not reliable. So it's better to use it on atoms, right? Also, EQ does not work for numeric atoms. Predicate functions list and null. In order to check whether it is a list, whether the list is null, you can probably go with these two predicate functions. So list takes one parameter, it returns true if the parameter is a list, otherwise it returns false. Null takes one parameter, it returns true if the parameter is the empty list, otherwise false. Note that null returns true if the parameter is empty. Member is another scheme function which takes an atom and a simple list and returns true if the atom is in the list. In order to check whether an atom is belonging to that particular list or not, we can probably use this member function. If the atom is in the list, it returns true, right? Otherwise, it returns false, right? For example, you want to check a particular member whether it belongs to list or not, right? How do we define? First, we are defining that function here, member function, with the help of define clause, member, atom, and list, right? So here, member is a function name, atom is the first parameter which you are passing as an item to check whether it belongs to the list which you are passed as the second parameter, right? So here the definition of the same is mentioned with the help of multiple selection statement conditional, right? So you can see the first predicate here in the conditional. We are checking whether the list is null. If it is null, then it returns false. But if it is not null, it carries some certain elements, then you are going to, apply car operation on the list. When you apply car operation on the list, what it returns you the head, nothing but the first element, right, of that list. And that, element is going to be compared with the atom that you're passing on argument. If both are equal, then it returns true. If not, you go to the else part, then what do? You are applying the CDR on the list because first item is already compared, no? So the remaining elements have to be compared. So the remainder part, you can get it by applying the CDR on the list. When you apply CDR on the list, you get the remainder part of the same. So you need to check whether the atom is available in the remainder part of that list. So you can see this is a recursive function. So again, you are calling in else part the same function, that is member, by passing the atom and the remainder part of the list. So again, you are going to check whether the list is null, or if not, then you are going to take the first element of the remainder list and then comparing it with atom. If so, then it returns true. Otherwise, you are further, reducing it, right, to take the further remainder part of that particular list, because you have compared first, that is the head part of the list, and the head of the remainder part also you have compared. Then you go for the subsequent remainder part of the same. So for that again you apply the CDR. So that way you will be recursively calling this function until you either return false with or you return with true. Fine. If it is found, then you return with true. Otherwise, you will be returning it with false. Right? Another here function defined to check whether two lists are equal or not. You want to check two lists are equal or not. So how do you check that? We can define the function here. The function name is equal sim, taking first parameter as list 1, second as list 2. Then with the help of multiple selection condition statement, you are trying to define the code for the same, where you are trying to check the logic of to ensure that whether these two lists are same or not. So for that, what you have to do, you have to take the first element of the list and first element of the list 2. Both have to be compared. And if they are equal, then you take the second element of the list 1 and the second element of the list 2. And if they are equal, then you move further like that until the last elements of these lists are being compared, and then they are found to be same. Then you are going to return it as true. Otherwise, you are going to return false, right? So first here you are going with exceptions also to be rather added, because if the list that you are passing as parameters, if they are null, then you have to return false, right? So the possibilities wherein you have to return false are, if let us say list 1 is false or list 2 is false, fine, then you have to return false, right? Then here when you are comparing, you need to first take the first element of the list. With the help of car operation, you can get the first element of the list 1 and list 2. So you are applying car operation on both list 1 and list 2. Then you are applying the predicate function equal to ensure whether they are equal, right? If they are equal, then you have to again call this function recursively by sending the subsequent list the remainder part of the list, right, of 1 and 2, right? By applying CDR function, you are again passing the remainder part of that particular list to this particular equal sim, which is going to be further checked to ensure that whether the element of the list, first element of the remainder part, is equal or not. If it is equal, then the further remainder you have to pass to the same and then check. So you have to do this how long? Until all the elements are compared, right? When all the elements are compared and they are all found to be equal, then you are going to return it as true. And if none of the situation being encountered, also you are going to return it as false, right? This is how you can probably define the code for many of the logics with the help of the car and CDR. Car and CDR are considered to be the basic functions on lists, right, in functional programming language. Another function equal here. This equal function takes two general lists as parameters and returns true if the two lists are equal. Otherwise, it returns false here. Fine. So you can see here elaborated with the same equal sim. So this equal function taking two lists as arguments, checking first the availability of the elements in the list here. If they are not at all the list, right, then you will return false. Or if they are not equal, also you return false. See, list 1 must be a list first, list 2 must be a list first, and both if are not equal, fine, also you have to return false, right? So now after checking that both of them are having the element and both of them are found to be list, here you are checking whether both of them are list, here you are checking whether they are null or not. So they are not null, they are list, then you go with the logic here. So what is that you are going to do? You are going to apply the same logic here that you have applied here, right? And then compare whether both the lists are equal or not, right? And append function, it takes two lists as parameter, returns the first parameter list with the element of the second parameter list appended at the end. So how are you going to define this append function? You can see here append is the function name here, and the list1, list2 are two parameters that you're passing. With the help of multiple selection, statement, control statement, conditional. The first predicate we are checking here whether to see the list1 is null. If the list1 is null, then probably list2 will be the appended one, because when nothing is there in the list1, nothing to be appended to list2. So the list which is going to be generated to have both the lists will have only list2. But let us say if list2 is empty, list1 is of course the result, right? So else, you are saying that is being combined in the else part here. You are passing list1 to car function. So car will give you the first element of the list, and then here you are recursively calling the append function by passing CDR of list1. It means the remainder part of the list1. Fine. See, when you are applying car list1, you get the first element here. The first element is available here, which is required to be rather appended. To whom it has to be appended, that is coming from this particular one, which is nothing but a recursive one, where you are passing CDR on list1 and list2 as it is. So what happens when it comes here? It again takes the first element of that remainder part. So first element of the first list and the second element of the first list also comes. So until it is null, it applies this. When once it is null, then list2 will be appended. So list1, all individual elements you have got here already. Then when you reach with list1 null, list2 will be written. That list2 will be appended to all the elements that you have already made it available through this particular function here. Then both the elements be rather appended. So automatically you can see when list2 null is also being taken care here. Okay. You can see the let function. Let generally when you want to define certain value to a variable which is going to be used in the further code of the same function, you can use the let. Fine. Like kind of assuming certain values for variables which you want to use it in the further code of the same, right? So just say let, and the variable to which you want to rather bind with certain expression, you can just say that, right? This this variable is binded with this variable is binded. Like that, you can have any number of variables to be rather binded with certain values or certain expressions, right? Define quadratic roots of a quadratic expression you want to find. Okay, how do you write the function to find the roots of a quadratic expression? You can see here the demonstration of the same is done with the help of let here. Quadratic roots is the function name. You have parameters a, b, c, and let you're saying a root part over to a. I mean, basically you will have discriminant part and you have the remainder part, right? So root part under root, what do you have? B square minus 4ac, right? Root part over 2a by square root of b square minus 4ac 2a. So here what is going to be done in this particular mathematical expression? What happens? This is the mathematical function by, and this is your first operand, this is your second operand. What is the first operand here? Square root of b square minus 4ac. So under root b square minus 4ac by 2 into a. Okay, under root b square minus 4ac by 2 into a is nothing but what? Under root b square minus by 2a. Okay, this whole you have considered as root over part. Okay, and this has been defined as a variable here, right? This variable has been evaluated to this expression rather, right? Now minus b over 2a. Minus b over 2a is evaluated to be like this. By you have, and here this is minus 0b. Right, so 0 minus b by 2 into a. by minus b by 2 into a, right? This is minus b over 2a. Now you have a display function consists of plus is the operation, minus b over 2a is one atom as the first parameter, and another parameter is root part over 2a, right? So this will give you the first root. So the first root that we are displaying as, what is it? Minus b by 2a. Here it is plus root part over 2a is nothing but under root b square minus 4ac by 2a. That's it, right? This is the root 1, right? And this is the second root. So in second root, what is that you're saying? You just change the sign here, right? You said minus b by 2a. This is the first parameter. On this first parameter and second, this is your first operand and this is your second operand. The operation to be applied are minus, right? So minus b by 2a minus under root b square minus 4ac by 2a, right? This is considered to be your root 2, right? Which you are displaying. Got it? So this since these two parts are common for the roots, this whole to be evaluated and represented as root part over 2a, and minus b by 2a is being evaluated and represented as minus b over 2a. So with the help of this lit, what you can do is you can evaluate certain expression and represent it as a variable which can be further used in the code. So in the further code, I can see I have directly used this lit variables, right? So I said that plus minus b over 2a, root part over 2a. It means what happens? This minus b over 2a will be replaced with the expression that you have defined for the same with the help of that let, right? So that way, what you can do is you can use this let to represent certain expressions once evaluated can be used wherever you want, right?